So moving on, we'll go to the second talk. It's by Anand Sarwate, a faculty member here, on a new NSF project, I think.
Yeah, this is a project that we have funded through the RINGS program. Roy is actually the PI, so all questions should just go to Roy. But now that Roy's retired, he's not allowed to be the PI. So somehow I'm like shanghaied into being the PI. All right. All right, so let's go with that. Right, so the project is called Real Time. Oh, I see. Oh, wait, okay. I'm having the same problem. You broke it.
I'm left-handed. It's not my fault. I was born this way.
Is it on? It's on.
Battery maybe dying.
It might be the battery. Hang on. It blinked. Nope. Oh, now it's blinking, but not doing anything. All right, I'll just stand here. All right, this way I have the safety of the podium in case you start throwing things. Okay, so the project is about timely inferences for edge cloud systems, and we threw in some words like resilient and autonomous and learning. But really, this is about machine learning, running machine learning applications on the edge, and then also trying to understand some of both the theoretical and then also some of the practical challenges that might arise in some future G scenario. So, what do we want in this project is to really think about what does it mean for an application to be operating in real time. And the motivation is several of us on the project work on machine learning. And the trend in machine learning is to larger and larger models, which take longer and take a lot of compute and and energy to both train and then actually run the inference at runtime. And then also issues that are common, of course, to everybody familiar in the room with all wireless systems, where you have time variation in the network, and so you're trying to build resilience now not just in terms of connectivity, but also in terms of the performance of these machine learning methods. And then so also, of course, there are always questions of privacy and security whenever you talk about anything involving data. So the goal and the core nugget of it is we want to be able to use machine learning to make sort of fast and accurate decisions. I say in these complex changing environments, but then also with efficiently, I guess, and we'll see what maybe try to understand what efficiently means. So we're looking at a kind of simplified model of what probably is really going to happen. We sort of think of three layers. We have mobile devices, which we think of as having, and since we're thinking about machine learning algorithms, we're thinking about how much compute and energy does it take to actually run these models. And I'll talk about timescale in a minute. So we think of them as having some moderate ability to do stuff themselves. So, currently a lot of ways that at least I've seen people think about doing sort of large scale AI supported applications. You kind of treat the device, the end device, as like a sensor, more like a sensor that's going to send the data to the cloud, which is going to then do the evaluation. But if you want to do something at a faster time scale, you're going to have to try to do as much as you can on the device as possible. And then we have these edge cloud instances, which have a kind of we think of as having a low latency, because this project is really about understanding latency, where I say lower latency to these devices. And then there's kind of a bigger cloud, scarier looking cloud in the back, less friendly colored. By the way, this talk obeys my meta theorem, which is that if I can't explain what I'm doing in emojis, then I've failed. Emojis, boxes, and arrows. Okay. And so also, there are also lots of other things that we could think of as we think of things like doing handoff and peer-to-peer connections, or being connected to multiple edges, and that all is additional complications, which one question we're trying to ask is what is that going to say in the context of running machine learning methods? So, as I alluded to before, from the theory standpoint, because I'm sort of more of a theory person, right? Is try to think about is that the machine learning models are very large. If you look at these large language models, I don't know if anybody's played around with some of these large language models or DALL-E or those kind of things. They're huge. Or GPT, right? gazillions of parameters, and it's not just the training. People focus a lot on the training. Oh, it takes like weeks to train this model and it requires, scads of data, but it also takes a lot to run, to actually evaluate the label. To get the actual label is, requires, say, installing the mod, if you want to do it on device, you'd have to install that model on the device, install those gazillions of parameters and run this neural network on the device. And so that's pretty of a big ask. The other thing that it's a big ask is that if you want to run everything on the device, it might not be fast enough to run everything. So it might not have the compute power, it might not have the storage, but it might not be able to do the compute fast enough. But also just asking the cloud to do your evaluations, outsourcing all your computation to the cloud is not effective, right? It's not going to, it's going to lead to high latency because this backhaul has high latency. A third aspect that I think Wahid, if he's here, is really, well, I guess he's not here. Okay, he was here. Is concerned about is about the time variation in the model. So that is in a wireless system, you might have adapted. If we're thinking about using machine learning methods to do things, the thing that gets all the attention that you see on Twitter, I guess before Twitter imploded, was all of the was kind of these train once and then test models. So you spend a lot of time training this model, then you have it, it's done, and it works. It isn't adaptive. It doesn't adapt itself, and we want to think about applications where you have to be adaptive and adapted in particular to time varying scenarios. And then finally, of course, if you want to train some of these models, you have to collect data, and the data that you collect is going to be collected from individuals, and so there's some privacy concerns here as well. And there's also the project, as I said, is this NSF project funded by the RINGS program. And so we're looking at algorithms in decentralized, we think of decentralized and distributed learning problems. So people tend to say Google's been very successful at marketing this term federated learning, which I think everybody used to call just like distributed learning 20 years ago. It's the same thing, but now it's called federated learning. So I'm going to say federated learning. Everybody's excited about it. So we're thinking about, but I think there's something beyond what people typically think of when they think of federated learning. And I'm happy to talk about that a little bit more. From the privacy perspective, which is what I work on a lot, is trying to understand where do the privacy concerns arise, and then how do we quantify what privacy is in these applications? Because privacy in the context of the U.S. Census is different than privacy in the context of sort of a real-time application, where our location privacy is also different from that. So we have to think about those things. And then also Roy is very interested in understanding what does it mean to be timely, because he's spent a lot of time working on timeliness in machine learning systems. And then Ray, of course, wants to know if it's going to work. And so, I can sit here and do a bunch of proofs and theorems, but it might not actually mean anything in the end if it doesn't work, right? I'll have a good time at least, though. Okay, so I want to talk about timescales, because one thing that when you sat down to think about this problem is they're kind of these. I don't want to use like a thinking fast and slow metaphor here, but like there's 3 timescales to think about. One is sort of tens of millisecond level real-time operation, where you want to have a label spit back to you very fast. So that you can do something like play a video game or do some VR application. Then there's a second sort of slightly slower level, which you can think of as like online, which you can think of as this is the like model drift. So if let's say caused by mobility, I move from one region to another, that say the channel is going to change. We know that like from wireless that the channel is going to change. So also the way either the specific classifier that we run, or we have to adapt it, will change, or we have to adapt the classifier that we have in the face of collecting new data. But that's happening at sort of medium time scale. And then there's the sort of traditional, if I go and take a machine learning class, I go and I use the cluster and I train my machine learning model for a few hours, and that's we think of that as being kind of pretty much offline. And if you think about the machine learning pipeline, when we do it, take a machine learning class, you first do model training that's entirely done offline. People do talk about online learning for model adaptation, but they actually, a lot of the work in online learning is about kind of doing this offline thing more efficiently. So for example, stochastic gradient descent is just, starts out thinking about it as, oh, it's an online learning method, but it's really used to train offline models. We're not doing that, but oh, sorry, this should be online. So the model testing, you should be, is the fast time scale. So you're going to be, this is at test time, at runtime, you're going to have to evaluate the output of the neural network on some input data. And that's going to, again, that can also be costly. And I think it's underappreciated. It's a little bit underappreciated how costly computing the label can be because we're excited about what we're excited to see what the machine learning model produces, but we are not asking for those decisions to be happening at a very fast time scale. So the challenges are again on both sides. So training machine learning models is very challenging because all of these sort of high flashy applications and also a lot of the future envisioned applications, like these foundation models, are very data hungry. And so they're going to need a lot of training data. Now there's advantages and disadvantages here because we have millions of billions of mobile users. So we have like an opportunity to collect lots and lots of data during real-time operation. To train these things, but we still have to, it's still a challenge on how to make that scalable. So we can't retrain systems regularly, and we'll have to adapt. And this is where federated learning comes in. This is why everybody's excited about federated learning. The idea being that you're not going to completely retrain your model. You're going to tune your model over time, having collected data from users. You get to see what their next word prediction selections are. Collect that over the week, and then it gets sent back to Google, and Google creates, updates their model and pushes it out in a software update. So that's happening. That's one type of thing there. And then on the other side with the on test time, the thing that we're focusing on is that we can't afford to actually use these large models all the time. So we have to come up with either a way. We have to come up with a way of being able to use these sort of large models as needed. That's the kind of, and the question is, what does it mean by as needed? So there's been a lot of work done on all. So the project kind of incorporates these three aspects of kind of understanding the trade-off between latency and learning accuracy and prediction and machine learning, and then privacy. But we don't, for example, in machine learning methods or training methods, you don't see models which are specifically optimized to produce decisions fast or introduce latency or any kind of constraint into the training. So one thing we're trying to look into and trying to understand is, can we incorporate in the training of the model, or either in the architecture or in the optimization that we set up, can we ask it to balance some sort of latency requirement? And there's some work on this that's been done on in other areas that can be kind of cast into this framework, which I think is pretty exciting. There's a lot of work on machine learning, privacy preserving machine learning. I've been working on that area for maybe 12 years now. But privacy in, differential privacy, for example, which is like the very popular framework for privacy, is really about best suited to things like the US Census, where you collect the data, you can identify individual records with individuals, and then you're going to then publish something once and then done, right? As opposed to a system where you're, I don't know, in a few minutes you're going to be asking for a couple hundreds or thousands of decisions, or possibly sending that much, sending things that many times to a third-party service. And in terms of the third aspect on age, the work, the sort of great work that Roy's been doing has and follow-on work has focused a lot on just the timeliness of the decision making of the update, and not about the content. There's no it's agnostic to the content of what the update is. But now there is if I'm trying to make many decisions, hundreds of decisions per second, or couple hundred decisions per second, what does it mean then for these, if these updates are decisions from machine learning methods, and in fact they say potentially they're correlated over time, so actually maybe it doesn't, I don't think of every update as equal. That's one question that we could ask, right? And these three things have not sort of been, I think, tested in the kind of way that people in this room like to test things, like on a test bed, like Cosmos. So we're thinking about this. The goal is to build sort of this what is taking developing machine learning models that can be split across the mobile and the edge, so that you can you sort of train a two-headed thing, one part of which is suitable for running on the mobile device and could be kind of run most of the time, like say on a good day, will kind of run on its own and be able to produce reasonable looking decisions, and occasionally then would ask for help from the edge, which has more compute ability. And the idea is then that we can, it's still a little bit slower to ask the edge, and if the edge has to then ask the center, if you like, then that's okay, as long as it doesn't happen too often. So that's the kind of thing that we're looking at, right? And so the way to balance that, is to try and understand how age of information and how these sort of age-aware communication is going to play a role in helping you with that balance. In terms of privacy, you have to develop new privacy metrics or adapt existing privacy metrics to understand what they mean in the context of real-time operation. In particular, we're worried about when we talk about privacy, we're worried about privacy because we're worried that somebody's going to do something with the bad to us with the data. Now, if so, in some scenarios that is time bound. So, for example, I might not want you to know where I am right now, but I might not mind if a week from now you know where I was. I might mind less. So trying to understand what are the ways to sort of incorporate that, and as we do with existing machine learning or existing privacy models into machine learning training is an interesting idea. And then we want to try and again test these things out on Cosmos to see if we can what we design on paper is feasible. So on the first part I said we're trying to split the machine learning model across the device and the edge. And I would say that a lot of existing work has focused on taking a big model and then pruning it or trying to shrink it to make it fit onto a mobile device or some lower compute a device which has a sort of more limited computing capability. So I think we want to do is understand that there should be something more than that we can do. That it's not about taking a big thing and then kind of shrinking it down, but maybe we can actually from scratch train two models at the same time that can work together compatibly. That's the question that we want to ask. So the constraints that we have on these, what we're thinking of as device, the one that runs on the device is that it has to be small. I say 1 to 10 milliseconds. That seems very optimistic. It's super optimistic. Let's say tens of milliseconds. But per instance inference. So we want to be able to make a decision, get a label from a classifier, at a pretty fast time scale. we're okay with making some errors, because that's the other thing about machine learning methods, is that there's always some probability of error. And sometimes if you look at the papers, the error probability is pretty high. The error rate is pretty high. And that can be okay if you have, I guess, if the what am I trying to say? The consequences of making an error are not huge. And so this is actually different. I mean, I come from an information theory background, so I want my bit error rate to be super low so that I can do my error correction and stuff like that. But here the error rate can still be like 20% or something like that. We should still be able to do something interesting. Right? That'd be a hope. And then we want to be able to adapt these models over time based on things like the channel condition, but also other test time environmental issues. So in terms of in the context of age of information, you have these for machine learning. Now we're thinking about a source as generating timestamped inference jobs. So that is, the device is saying, okay, I have a job for you, Edge. Please give me a label. And then, of course, there are multiple users, so those jobs are going to have to get scheduled. So there's a sort of scheduling and issue that's going to come up there. And then after the you run the machine learning model, you get an update, and then you have to try to quantify how stale is your update. So what is the actual latency we also have to sort of think about what happens for when the decision is fed back. And so in this scenario, you have like questions at multiple levels. You have questions about like how do you manage multiple users, but also just how do you think about the idea that the inference jobs, if I'm okay with making some mistakes, I might also be okay with like not executing some of them. So the question is like, how should we build that flexibility in it? In the network, for the privacy perspective, thinking about the 3 timescales, as I said, we have to sort of rethink what we mean. What do we want out of a privacy metric, and also what the side channels are that are leaking information. And so in real time, you have these sort of the events the traffic itself can leak information. So if I have a scenario where I have a device which is asking for help, maybe the act of asking for help that is asking for help from the edge cloud, maybe that is actually revealing something about my state that I don't want to reveal. So there is the more I ask for help, the more I reveal about my internal state, and maybe that's something we should try and understand. So that provides another constraint on the communication between the mobile and the edge. How should I go ahead? Okay, great. And then we have this online learning stuff, which is similar to federated learning, as I said before. And then we also have offline learning, which I think is more traditionally kind of the realm of differential privacy. But we're kind of interested in the real-time questions here. And then we have to do a lot of careful design for the architecture in order to both test this thing and also to try and understand how these kind of systems with the machine learning, coordinating the system with machine learning, what does it require in terms of things like real-time orchestration and load balancing and so on. We are thinking about this Cosmos Smart intersection. We've been spending a lot of time in our project meetings, like discussing it. I don't know if the students are really excited about it, but I think one thing that we don't want to be limited to this, thinking about this, because there are a lot of interesting applications, I think, in stuff like industrial monitoring and smart buildings and other scenarios where it's not phones playing video games, which is I think the other application that we're thinking about, smart intersection and phones playing video games. But there's a lot of stuff in between that are on the elsewhere where I think this framework would be very useful. Okay, so I think since I'm running out of time, I have some questions here, and maybe I'll just leave up these questions here, because I think that's kind of like what I wanted to do is sort of present what we're thinking about now. We're just starting this project. It's just kind of getting off the ground. So I'm happy to get some insight from you about what you might think of these questions, or what do you think is maybe a different question that we should be asking that we're not asking. Yeah, thanks.
Thank you, Anand. We can take a few questions.
Yeah, but
So I have a question for you. Right founded.
Mhm.
So we know that tons of works.
Yeah.
You
Right.
mentioned that for some type of patients, it's the consequence of actually talk. Whatever I was wondering, which type of patient?
so if I'm trying to if you're thinking about video, right? You want to say you want to find a bounding box on some object region of interest, right? It's okay if some frames you're kind of, glitches are okay, as long as like over kind of a longer time course, you're fine. And so the question is, it's not like if I send you 1,000 frames of video, and 20% of them are kind of the region of interest is like not identified correctly, it probably isn't going to matter in terms of the performance, the experiential performance for the user, as opposed to if I have 20% bit errors, then I have to suddenly use an error correcting code with if I need to get all the labels 100% accurate, that is, I need to be able to decode them and error correct them. That's a different question, and so that's the distinction I'm trying to make here.
Yes.
To train models and to collect all the data and what have you, it is very expensive and takes a lot of effort.
Yeah.
So that can certainly be centralized. But is there a possibility for having some canonical model, that get developed over time?
Yep.
So just say use this canonical model. So,
Yeah, I mean that would be that.
And it could even be a combination of the canonical models, because I would suspect, this is a conjecture, a limited number of canonical models may suffice for the market.
Yeah, so I think that would be. I guess you're saying in terms of the architecture of the neural network or something like that, or the like pre-trained model.
The model itself.
Yeah, so definitely pre-training models offline, and then having, say, a library of them that are kind of for different environments, for example. That would be a great, I think, way to seed the system, and then you can collect data and during operation to try and either tune them or create new models later on.
Okay, we'll take one more question.
So this is, when you talk about privacy, I'm just trying to understand the model you have in mind. Because if you're uploading some training to the edge cloud, you're assuming there is a provider providing this.
So there's a couple different models we can think about, right? It depends on who's doing the labeling. And so if it's, for example, an application, and you have you might have a third party, software, ML as a service thing running on your edge cloud, that's a different, it might be that you don't trust the third party computing solution. On the other hand, if it's the network operator, maybe you do trust them because you have a contract with them, and they've already made some assurances to you about protecting your privacy. So this actually comes up in differential privacy. For example, the distinction between local privacy and what they call centralized privacy. So the question is, do you trust the data collector or not? And so that's.
So that it's similar. You think it's similar to location service in terms of keeping your.
So yeah, it can be. It can. So there are going to be similar. I think there's similarities to location services, and then there are also similarities to more security-like questions. Like, for example, if I know so one thing, and I guess I'll talk about this later in the afternoon, like keystroke, the timing between keystrokes, you can infer somebody's password from the timing between keystrokes. So there's like this kind of fine-grained time information. That side channel also leaks information of a different type than location would.
Okay, thank you, Anand.